Check it out now, y'all.
NanoHub U, online instruction.
In this lecture, we'd like to try to understand a little bit more detail how it can be that the length of a moving object is contracted. And ultimately, I think the answer to that question comes back to the fact that this concept of simultaneity has to be discarded when you discuss objects that are moving close to the speed of light. So very often you'll see this discussed in textbooks under the term simultaneity becomes relative. And would like to just go through a discussion to try to allow you to appreciate what that string of words actually means. Now, these measurements that we're talking about are rather complicated, and I like to make the point that to make these measurements, you're going to need to go to a special lab, right? And that special lab is going to contain a reference frame in it. And this reference frame, you have to sort of sit back and close your eyes and imagine what this reference frame lab might look like. But what it ultimately has to appear, what it ultimately has to contain is it has to contain some sort of a grid that allows you to measure positions conveniently at X, Y, and Z, right? And at each point in that grid, you also happen to have some sort of a clock that you can measure times that occur at that particular point in the grid. So, you know, a lot of these experiments are thought experiments, and they rely on your ability to measure position and time at different points in space and compare that to another reference frame that moves by at a speed comparable to the speed of light. How do you make those measurements? Well, you make those measurements by building some sort of a relativistic reference frame laboratory. And that's sort of an underlying theme of all these discussions. We assume that you can make those measurements easily, maybe not in your own home, but by going to a lab that's equipped in this way. So that's an underlying assumption in these entire discussions of special relativity that at least you should be aware of, right? You should be aware of that you need some sort of a lab like this to make these measurements that we're discussing. What I like to do is I like to discuss now the idea of simultaneity, and like to set that problem up. And the way I like to set it up is I like you to consider two clocks. Of course, these represent light clocks, and they're at different positions, let's say x1 prime and x2 prime in this reference frame S prime. So this observer in reference frame S prime is at rest with respect to these two clocks, and by various techniques, he can synchronize them so that the arrow in each clock points straight up at, let's say, sometime t0 prime. And then sometime later, t prime, right, the position of this arrow, or the number of ticks that require the clock to go from t0 to t prime, is exactly the same for both of these clocks, x1 prime and x2 prime, that are located at a distance apart one from the other. And so what we say is, by this process, we say these two clocks are synchronized. And clearly you can do that, right? It's not hard, because you could bring this clock to the same position as that clock. You could synchronize the two times, and then you could take this clock, move it to position x2 prime. And if the clocks are made by a reliable company, right, they'll keep time in exactly the same way, and they'll stay synchronized as time moves forward. Okay? Now, the problem is, what happens if you ask the question, what does this observer see when he looks at these two clocks, right? And the key point is, these two clocks are located now at different positions. So what do you have to do in order to find the time intervals or the corresponding times that this guy would see on clock at position x1 prime and time he would see it on the clock position at x2 prime. Well, you have to use the Lorentz-Einstein transformation equations, which take you from the prime frame back to the unprimed frame. And in particular, in this case, we're interested in time transformations. So we have to use this particular formula. And I just apply that formula on this slide to the situation. I asked, what time does the guy measure on clock at the position x1 prime? And it's going to be given by this expression here, where t prime is the time that the observer in the reference frame s prime would measure. Okay? And likewise, the time that the observer in the S frame measures on the clock at position x2 prime would be equal to gamma times the time t prime that the observer in the reference frame S prime measures, plus this correction term that depends on the position of the clock in the primed reference frame. That position is x2 prime, right? And so then we can ask the question, what's the difference in these two times, right? The observer in reference frame S measures. Well, in the S prime frame, right? In the S prime frame, there's no difference between T prime and these two clocks. So when I do the subtraction, right? When I do the subtraction on the left-hand side, you're just going to get the time difference that the observer in frame S measures, right? When I do the subtraction on the right-hand side of the equation, the T primes are going to drop out, right? But you're not going to get zero. That's the key point here, right? So in the S prime frame, you would say there's no time difference between the two clocks because T prime is the same for both clocks. In the stationary frame S, there's a term that depends on the difference in location of the two clocks. And so two clocks that are synchronized and simultaneous, one with the other in a reference frame S prime, when viewed from a reference frame S, now show a time difference, right? And that just simply means that this concept of simultaneity is a relative concept and it can't be enforced. It's not a meaningful quantity. It depends on what reference frame you're viewing the clocks, right? That's the basic idea. So the expression or the term that the proportionality that relates the difference in time in the S frame is related to this parameter gamma times beta. And I list a table so you can see the sorts of numbers that you're expecting, right? If the speed of the reference frame V sub f is equal to 0.1 times the speed of light, then this factor gamma times beta is a small number. It's about 10%, right? And it just means that the two clocks are going to appear to be out of sync. They actually are. They're not synchronized anymore, but it's a 10% effect. As the speed of the reference frame S prime increases, as V sub f gets larger and larger, you can see this factor gamma times beta continues to increase, right? And increases without bound as V sub f gets closer and closer to the speed of light. So the lack of synchronization becomes a very serious problem whenever this reference frame is moving very fast with respect to the speed of light. So in order to help you appreciate some of the subtleties of this discussion that we just conducted, it's important for you to be able to distinguish between different situations that are very closely related. And perhaps if you read the textbooks, you won't pick up on the fact that sometimes we're talking in one set of terms, and in another problem we're talking in a completely different set of terms. And sometimes it's very confusing unless you see this discussion or you appreciate this discussion that I'm about to have, right? So I just want to talk about the problem of synchronizing clocks in two reference frames. And I'll say that if we have a sequence of light clocks that are located in a reference frame and one relativistic laboratory located in the frame S prime, and we have another set of clocks located periodically along a reference frame in a relativistic lab located in the frame S, if the relative velocity between these two frames is 0, then it is possible to synchronize all these clocks one with respect to another. That's not a problem, right? The difficulty, so you can, for instance, you can set all the clocks so that they measure 0 at some instant in time, right? They're all synchronized. All these clocks are synchronized with all these clocks. And that's simply a result of the fact that there's no relative velocity between the two. Okay? Now, when you start to let S prime acquire a velocity and fly by frame S, an important question turns out to be, does the observer in one frame watch all the clocks in the other frame, or does he just watch one clock in the other frame, right? And it's a subtle distinction, but it's an important one that you have to appreciate. And so I like to just go through the different possibilities so that you can understand the situation. So now what I'm doing is I'm letting frame S prime have a velocity v sub f. This is our standard standard geometry. Here's my rest observer down here in frame S. We consider this to be the reference frame, right? Now remember, all these clocks were originally synchronized, and all these clocks are identical, so they're all keeping time at exactly the same rate, right? And our friend down here in the stationary reference frame S sees all the clocks synchronized along the x-axis. But as he looks at each clock in the S prime reference frame, right, if he compares the time for the equivalent clock in his reference frame to the clock, to the appropriate clock in the moving reference frame, what is he going to see? Well, he has to go back, right? He has to go back to the Lorentz-Einstein transformation equations that describe how time is transformed. And that the Einstein transformation, the Lorentz-Einstein transformation equation is given by this equation here, right? And in particular, this time t on the clock in the S frame is precisely set equal to 0, let's say, right? That means you can set t equal to 0 in this frame, in this equation, and that the equivalent time that this guy would see in the moving reference frame is then just going to be given by this expression. And you can see that the time t prime that this guy would measure for each of these clocks is now going to depend on the position x. And so if x is a positive number, right, this negative sign is important, because if x is a positive number, that means clocks out here in the positive x direction are going to be behind the t equals 0 mark. And when x is a negative number multiplied by this negative sign gives you a positive number. That means that clocks in the negative x direction are going to be running ahead of the clock that's, let's say, synchronized at t equal to 0 in this frame. So if this observer is looking at all the clocks, right, he would see that there's no synchronization of the clocks in this reference frame whatsoever. The other point I'll make is notice that if x is equal to 0, right, then the two clocks are in fact synchronized, right? So if this clock at x equal to 0 reads t equal to 0, then also this clock at x prime equal to 0 also reads t equal to 0. And of course, that's an assumption we've been making all along. We always say that the two clocks at the origin are synchronized as the two frames coincide one with respect to another. So we've made that implicit assumption numerous times in the discussion of special relativity, and it sort of falls out from this discussion right here. Okay, so that's the case when reference frame S is fixed and S prime is moving. But you can just turn the problem around, because it's just as valid to treat S prime as a stationary reference frame, and then ask what would the observer in S prime see as S acquires a velocity with respect to S prime. Well, if S prime is the rest frame, then S has to acquire a velocity, and to achieve the exact same results, S has to be moving in the negative X direction, right? X has to be moving in a negative X direction if you consider this to be the rest frame. And that's what I've got shown in this diagram. So now the guy in the rest frame is now, this is the frame S, right? And he sees all of his clocks being synchronized at t equal to 0. He'll see this moving reference frame zooming by him in the negative X direction at a velocity v sub f. And with his reference frame laboratory, he can measure the times on the clocks at different positions along the X prime axis. He's going to get, he wants to know what time he will see, and he has to use the Lorentz-Einstein transformation equation to sort that out. All his clocks are synchronized at t equal to 0, so you can put t equal to 0 in this expression. What you've got is you've got a negative sign. The velocity is now in a negative direction, so those two negative signs cancel out, and he would see a time in his reference frame that is ahead of t equal to 0 if x prime is a positive number, right? So for clocks in the positive x direction, he would see that they're running ahead of time, and for clocks in the negative x direction, he would see they're running behind time. And it just follows from this equation right here, right? And depending on how far ahead or how far behind they appear to be, just clearly depends on the location x that this guy would determine the clocks to be at, right? So again, you get to the same conclusion. Clocks that are synchronized or simultaneous in one frame, they're not simultaneously when you look at another frame. And this is the situation when you're looking at all the clocks in parallel, right? You're trying to understand the times on all the clocks. The other situation is the one in which an observer just watches one clock, okay? Now, when you just watch one clock, that clock is at a fixed position x0 prime, right? And the transformation between the time measured in the S prime system and the time measured in the S system is again given by the Lorentz-Einstein transformation equation. But this quantity now is a fixed number. It's a constant because this clock is at one position. So this is referred to as a point event. We talked about point events last week, right? When you take the time difference, right, that this guy, the guy in the S prime frame measures, right, he measures a time difference delta t prime. You ask, what is the time difference, the equivalent time difference measured in the frame S? That's delta t. So when you take the difference between t and t plus delta t in this expression, this quantity cancels out, and this is how you get the time dilation formula that we've talked about, right? And then of course you can flip the problem around, and you can reverse the reference frames, because you could just as well imagine this reference frame is fixed and this reference frame is moving. If this reference frame is moving with respect to this one, it has to be moving in a negative direction, and that's the situation I've got drawn here. Right, so now all these clocks are synchronized, and the guy in the reference frame S measures a time interval delta t. He wants to compare that time interval delta t to a clock located at a position x0 prime in the primed reference frame. He has to use the Lorentz-Einstein transformation equation. Again, this term is a constant number, right? Because this clock x0 prime is at one point. And so then you again find that there's a time dilation between the two reference frames that's related to the value of gamma that characterizes these reference frames. Okay? So Hopefully that discussion doesn't confuse you. Hopefully it gives you some insight into what's going on. To help sort things out, there's a definition called proper time and proper length, and it's important for you to know these words, right? Because you'll see it in all the textbooks. Proper time is the time interval recorded between events that occur at the same location, right? So if you measure an event and you measure how long it takes for an event to occur, and that measurement is at exactly the same location, that's referred to as the proper time. There's also something called the proper length, and the proper length is the length measured of an object. It's the length of an object measured by an observer that's at rest with respect to the ruler that used to make that measurement. So if there's no relative motion between the object and the ruler, that's referred to as the proper length. So the proper length and the proper time could be in different reference frames, and so you can't be confused about that, right? You can't be confused about that. You just have to apply these definitions, and it's an attempt to provide a code word. Whenever you see proper time or proper length, that's a code word that's trying to tell you that that helps you to distinguish that this is the situation that's being discussed. So the bottom line from this lecture and the previous lecture is the time dilation and the length contraction formulas. You're going to have to know how to use those if you're going to demonstrate understanding of this particular topic. So as a final example, right, one last attempt to try and explain this, I'd like to discuss the measurement process in terms of this lack of simultaneity and show you how these two concepts are related and how it can be that an observer in let's say a fixed reference frame measures a contracted length for two identical objects. So here we have two objects. Let's say one is a blue arrow, the other is a light blue arrow. When frame S prime and S are at rest, these arrows exactly are the same length. Let's say they're 40 meters, right? When S prime flies by the reference frame S, the observer in reference frame S determines that the length of this arrow is 20 meters. And the question is, how can that be, right? How can that be? So the way I try to explain it is I try to discuss the measurement process. And so the measurement process is as follows. This observer has to mark down on his rulers, right, on his ruler that's attached to his reference frame, where this arrow is as it speeds by, right? So initially he marks down a position x2 in his reference frame that corresponds to the front end of the ruler, okay, at point x2 prime in this reference frame. And at the same time he makes that measurement, he also records the time that a clock located at this position x2 prime reads. And so he says, oh, I made the measurement of the location of the front end of the arrow at the location, the front end of the arrow was at the point x2 prime at a time t prime, right? And then he very quickly looks and he says, okay, now I'm going to measure the back end of the arrow, the position of the back end of the arrow. I'm going to measure that at the exact same time that I measure the front end of the arrow, because that's how you make a measurement, right, of length. You have to measure the front and the back end at exactly the same time. So he looks and he says, oh, the back end of the arrow is here, okay? And so he's going to put a mark down on his ruler that says this is where the back end of the arrow is located. But he looks at the clock, right? And the clock is not synchronized with this clock because this whole reference frame is in motion. So in fact, the clock located at this point, which is where the back end of the arrow is, it reads some time t prime minus delta. So this observer says, oh, I can't make a measurement yet because it's not at exactly the same time. So what he has to do is he has to wait an additional time delta such that the clock located along this axis reads the same as the clock t prime that occurred when he made this measurement of the front end of the arrow. And then in that additional time that he has to wait, of course, the arrow is moving, right? So the arrow is moving. So when this clock located at the back end of the arrow finally reads the same time t prime as the clock that was located at the front end of the arrow when he makes this measurement, then he marks down the location of the back end of the arrow, okay? And in the process of doing that, right, and trying to make the measurement of the length of an object simultaneously, the front end and the back end at this exact same time, right, he gets this fact that the arrow is contracted in length, right? So I worked through the numbers here. What you find, of course, is you find whenever you get a factor of 2 in length contraction, you know immediately that the velocity is 0.866 times the speed of light. But I worked through the arithmetic at this just to work it out. So to me, this argument gives you some insight into how it's possible that the length of the arrow is contracted when the velocity is comparable to the speed of light. And ultimately, I like to believe it's related to the fact that you cannot have simultaneous synchronization of clocks in a moving reference frame. And that lack of synchronization causes you to make a measurement that forces you to believe that the length of an object is contracted when it's in motion. So if that helps, great. If it doesn't, you know, read some other textbook and try to sort it out so that you understand it in your own terms. Many explanations of these effects have been written up over the years. So please feel free to read other textbooks, because it's the only way you can come to some understanding of this material on your own. So I'm running a couple minutes late here. I got to stop. The next lecture, we're going to focus on experimental tests of time dilation. Before we leave the topic, I want to convince you that this is a real effect. Once you believe time dilation is real, then the length contraction follows. It's logically very tightly connected. So come on back and we'll show you one of the early tests for time dilation. We'll go through it and explain to you the details. So hopefully you'll have a better appreciation of how these strange equations are tested experimentally, and how the experimental tests do in fact verify these Lorentz-Einstein transformations. So see you when that lecture starts.